In this lesson, we'll be looking at one of the application of electrolysis, which is in extraction of metal. And we are using the extraction of aluminium as an example. So at the end of this lesson, you should be able to describe and explain the extraction of aluminium from purified aluminium oxide, which is called bauxite, by electrolysis. Also, you should be able to state the use of molten cryolite and the need to replace the positive electrode during electrolysis of aluminium. It's one area to focus on. And lastly, we'll try to write the ionic equations for the extractions of aluminium, especially looking at what takes place at the electrode, negative electrode, and the positive electrode, okay, with respect to the transfer of electron.
For aluminium oxide is one of the things important for you to know, Al2O3. Of course, you also need to know that the ore of aluminium is called bauxite. The ore of aluminium is called bauxite. Okay, so combined with oxygen, aluminium and oxygen will give us the aluminium oxide. So basically, the chemical formula for bauxite, it's aluminium oxide. Okay, so the extraction of aluminium, it's actually done by electrolysis. Okay, so via electrolysis, aluminium oxide is broken down into aluminium and oxygen. Aluminium and oxygen. So basically, refer back to the electrolysis of molten ionic compound that we did. It's a very simple electrolysis because each time it involves only one cation and one anion. So there is no competition at the electrode because you have one cation and one anion each migrating to the various electrode depending on their charge. Okay, another thing you need to recall is the fact that aluminium oxide, being an ionic compound, okay, has a very high melting point of over 2000 degrees Celsius. Okay, so basically, in order to be able to melt it, you need to dissolve it in molten, make it become molten by dissolving it in a compound called cryolite. So you need to know cryolite, requirement for electrolysis of aluminium, and of course the formula of cryolite is important for you to also note that Al3, Na3, Al(F)6. Okay, Na3, Al(F)6. So basically, when aluminium oxide is dissolved in cryolite, it lowers the melting point to about 1000 degrees Celsius. That's a great deal, about half of it, okay, it's gone. So it lowers the melting point, and of course the cost that will be required to generate electricity and heat energy to melt the aluminium oxide would have reduced. Okay, so you need to know that function of cryolite. So cryolite has a function here. It lowers the melting point of the aluminium oxide, and it essentially reduces the working temperature of the electrolytic tank. Another function of the cryolite is that it serves as solvent for dissolving aluminium oxide, and it also increases the electrical conductivity of aluminium oxide. Okay, so let's look at the electrolytic tank for electrolysis of aluminium. So you need to know the diagram for the electrolytic tank. Sometimes in questions it could be drawn and they will ask you to label it. So basically, the cathode here, which is your negative, okay, electrode, is made up of graphite. While the positive electrode, anode, is also made up of what? Made out of graphite. Okay, so you have graphite lining for the negative electrode, and the positive electrode, you have the graphite lining. We said something earlier about graphite carbon being an inert electrode. Okay, so that's the first thing to recognize. You have the positive electrode is made up of graphite blocks, okay, which hang over the tank, and of course the negative electrode is also made up of graphite lining, but the tank itself, of course, is made out of steel. Okay, so let's see the chemistry behind this. So the first thing that happens in this electrolysis is that aluminum oxide is dissolved in molten cryolite, and the function has been stated earlier. So basically, you have in the molten cryolite where you have the aluminum oxide. So in its molten form now, you have your aluminum oxide, Al2O3, okay, essentially split into aluminum ion and oxide ion. Okay, so you have only one cation there, which is the aluminum ion, and only one anion, which is the oxide ion. So there is no competition at the electrode. So basically, because like charges attract and on like charges repel, on like charges attract, so the aluminum ion will migrate to the negative electrode, okay, while the oxide migrate to the positive electrode. So looking at the electrode diagram properly, so you have your aluminum oxide migrating to this layer. This is where the aluminum oxide will migrate to, okay, the layers here, while your oxygen, that is the oxide ion, will migrate to the positive electrode that is just over the tank. So essentially there is already a pattern for separation there. Okay, so let's look at the next step here. The first thing, you have the positive ions attracted to the negative electrode, and I already showed you where the negative electrode. So the negative electrode is just at the bottom of the tank here. Okay, so the aluminum can settle there, it migrates there. So but your focus basically will be when the aluminum migrates and gets there, what will happen to the aluminum? Okay, when an ion migrates to the cathode, okay, what happens at the cathode? Remember cryo. What happens at the cathode? You have cryo, your cathode is reduction, and reduction, remember the oil rig, reduction is gain of electrons. So when the aluminum gets to this region, it's going to gain electron. So the aluminum, which carries a charge of 3+, we gain 3 moles of electron to be deposited as aluminum atoms. Okay, so from the liquid metal, it forms the liquid metal at the bottom. Okay, that process is actually reduction. Okay, so that's simple. Let's see what happened at the positive electrode. At the positive electrode, the oxide will migrate to the positive electrode, and so when the oxide gets to the positive electrode, it's going to be discharged as what? As oxygen. So at the positive electrode, which is the anode, what happened at anode? You have oxidation happening at anode. So when the oxygen gets to the anode, it's going to lose electron, because oxidation is the loss of electron. So one oxygen atom is going to lose 2 electrons. One oxygen atom will lose 2 electrons because oxygen is in group 6 and the valency is 2. So if it loses 2 electrons, it becomes oxygen atom. Because oxygen is diatomic, so you would expect that if 1 mole of oxygen, okay, loses 2 moles of electron, then 2 atoms of oxygen here will lose 4 electrons. Okay, so we can balance the equation this way. So 4 moles of electron is lost. So essentially we can see here that oxygen gas is what is released at the what? At the positive electrode, which is the anode, so the focus should be on trying to, so basically as the process continues, you have molten aluminum oxide that will be collected around here, being the negative electrode, will drip into a particular container. Here the molten aluminum will be tapped off, okay, while at this particular region you have the positive electrode made up of carbon, because oxygen will be the one that will be attracted or discharged here. Oxygen has a way of reacting with the carbon, okay. If the oxygen react with the carbon, which is the graphite, then it's going to be liberated as carbon, oxide, carbon dioxide, carbon monoxide, okay. Carbon oxide will be liberated. So when that happens, the graphite will dissolve gradually because it's being converted to gas that goes out, so the size of the graphite will reduce gradually. So that necessitates that the solid positive electrode in the electrolysis of aluminum is being replaced over and over, because the graphite, the carbon in the graphite, combines with oxygen that is discharged at the positive electrode to form carbon dioxide. So basically they need to just keep replacing the graphite electrode, which is the positive electrode, okay. So electrolysis of aluminum basically just have that demerit, replacing the graphite, and the electricity required, the cost of electricity required to melt bauxite, even when it is dissolved in molten cryolite, 1000 degrees Celsius is still pretty high for industry to maintain, okay. So essentially you need to be able to write equations for what happened at the electrode, and of course the negative electrode, and of course the positive electrode. So just to recap, at the negative electrode you have reduction, because that is your cathode. Negative electrode is the cathode, you have reduction at the cathode, while the positive electrode is the anode, you have what? Oxidation. So the anode here is made up of graphite, and that is carbon, and so because it combines with oxygen, it dissolves away gradually. So having the two equations, the next thing is just to find a way to balance the number of electrons. Number of electron gain will essentially be equal to the number of electron lost. So just to balance that, you could multiply this particular equation by 4 and multiply this one by what? By 3. So essentially we could have 12 moles of electron lost in each case. So the equation can be rewritten as 4 aluminum 3 plus 12 moles of electron to give 4 Al, and the other side could be 6 oxygen to give 3 O2 plus 12 moles of electron, just to balance the number of electron lost as against the number of electron gained. So in essence, the aluminum and oxygen has been separated, so aluminum oxide has been decomposed into aluminum and oxygen. So you may want to try out a few of these, fill in the gaps, and see how you can work with that. Okay, so just go over the main point that you've learned so far in this particular topic, extraction of aluminum. So just to recap quickly, you need to know what bauxite is, the ore of aluminum. You need to know the formula of cryolite and the function of cryolite. You need to know the equation at the anode, equation at the cathode, what finally happened to the positive electrode, which is the anode, and of course the product of the electrolysis. Thank you.